Hi everyone. So we are going to learn a new chapter today. We have two pictures here and these are what we call capacitors. So for chapter 2 we are going to learn about capacitor and dielectrics. So this is an overview of chapter 2. We are going to learn about capacitance, capacitors which are connected in series and parallel, and then charging and discharging process of capacitor, and finally we are going to learn about dielectric. So what is a capacitor? Capacitor is a device that is capable of storing electric charges or electric potential energy. It consists of two conducting plates which are separated by a small air gap or a thin insulator. The thin insulator is called dielectric, and examples of dielectric are mica, ceramics, paper and oil. The conducting plates that are mentioned here can be in the shape of cylindrical, spherical or parallel plate. The electrical symbol for a capacitor is this. You can also draw it like this. So if you see symbols like this in a circuit diagram, then that is meant to be a capacitor. So what is a capacitance C? The capacitance of a capacitor is defined as the ratio of the charge on either plate to the potential difference between them. And this definition can be written mathematically as C is equal to Q over V, where Q is the magnitude of the charge on either plate and V is the potential difference across the two plates. So capacitance is a scalar quantity and the unit is farad or capital F. So this equation C equals to Q over V can be rearranged to be written in the form of Q equals to CV. And if we say that C is constant, then we can get an expression between Q and V in which Q will be directly proportional to V. So let's look at example 1. When the potential difference between the plates of a capacitor is increased by 3.25 volts, the magnitude of the charge on each plate increases by 13.5 microcoulomb. What is the capacitance of this capacitor? So the question is asking us to find capacitance, which is capital C, and then we are given the potential difference across the plates, which is 3.25 volt. So we have V is equal to 3.25 V. So Q is equal to 13.5 microcoulomb. So we want to find capacitance C. So you can use the formula C is equal to Q over V and substitute in the values of Q and V. Q is 13.5 micro, so times 10 to the power of negative 6 divided by the potential difference, which is 3.25, and you will get the value of capacitance to be 4.15 times 10 to the power of negative 6 farad. Okay, now we are going to look at effective capacitance of capacitors which are connected in series and parallel. We are going to look at capacitors in series first. So the figure shows 3 capacitors which are connected in series to a battery of voltage V. So based on this diagram, the combination of these 3 capacitors that are connected in series is actually equivalent to this circuit here. The new capacitance is the combination of the 3 capacitors, and we call it as the effective capacitance or equivalent capacitance, CEF. The charge on the effective capacitance is called as the total charge, QT. And we also have a battery which supply a voltage V, and the voltage supplied is actually equal to the total voltage. When we have a complete circuit, electrons are transferred on the plates of the capacitors such that the magnitude of the charge Q on each plate is the same. So the total charge Q on the effective capacitor is QT, and then QT will be equal to Q1 and equal to Q2 and equal to Q3. So the potential difference across each capacitor C1, C2 and C3 are V1, V2 and V3 respectively. So initially we know that we have the equation for capacitance, which is C equal to Q over V, and this equation can be rearranged to get V is equal to Q over C. So we can write down the formula for V1, V2 and V3. So V1 will be Q1 over C1, and then V2 will be Q2 over C2, and V3 will be Q3 over C3. And we can also write down the expression for the total voltage, which will be Vt is equal to the total charge over Cf. And then once we have V1, V2, V3 and Vt, we can write down the total potential difference V is given by Vt is equal to V1 plus V2 plus V3. So if we have a capacitor which are connected in series, the total voltage will be the sum of all the individual voltage for each capacitor. And then we have already written the formula for each voltage. So Vt will be equal to Qt over Cf. And then V1 is Q1 over C1. V2 is Q2 over C2. And V3 is Q3 over C3. As we know, the charge Q on each plate is the same with the Qt, the total charge. So we can actually cancel out Qt, Q1, Q2 and Q3 because they are all equal to each other. And then we will finally get an equation which is 1 over Cf is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Therefore, the effective capacitance Cf for n capacitors in series is given by 1 over Cf is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over Cn. So if you have, for example, 5 capacitors, then you will write down the expression until you get 1 over C5. Now we are going to look at capacitors which are connected in parallel. The combination of these three capacitors which are connected in parallel is actually equivalent to this diagram here. So the new capacitance here is the combination of these three capacitors, and we call it as effective capacitance Cf. The charge for the effective capacitance is called the total charge Qt, and the total voltage for the effective capacitance is equal to the supply voltage by the battery. When we have capacitors which are connected in parallel, the potential difference across each capacitor will be the same as the supply voltage. Thus, the potential difference V on the effective capacitor can be written as Vt is equal to V1, equal to V2, and equal to V3. The charges stored by each capacitor C1, C2, and C3 are Q1, Q2, and Q3 respectively. Hence, we know that the formula of capacitance is C equals to QV, in which you can rearrange this formula to get Q as the subject. So Q is equal to CV. We have Q1, which is equal to C1 V1, Q2 equal to C2 V2, Q3 which is equal to C3 V3, and finally we have the total charge Qt which is equal to Cf Vt. So now we want to write the total charge Q on the effective capacitor. So Qt will be equal to Q1 plus Q2 plus Q3. And then we have written down the formula for each charge. So Qt is Cf Vt equal to C1 V1 plus C2 V2 plus C3 V3. And as we know, the potential difference across each capacitor is the same as the supply voltage. So we can actually cancel out Vt, V1, V2, V3. And finally, we will get the formula for C effective, which is C1 plus C2 plus C3. Therefore, the effective capacitance Cf for n capacitors in parallel is given by Cf is equal to C1 plus C2 plus C3 plus Cn. So now we are going to look at the comparison between capacitors which are connected in series and in parallel. So let's look at capacitors in series first. We will have 3 capacitors which are connected in series, and it is connected to a battery which will supply voltage V. And this circuit can also be equivalent to this diagram here, in which the total capacitors combined will be equal to C equivalent or C effective, and then the voltage supply will be equal to the total voltage for the circuit. So to find the total charge, try to imagine we have a battery. Electrons will be flowing from the negative terminal of the battery, moving along the circuit, and then it will reach each capacitor. So from here, we will get Qt is equal to Q1 and equal to Q2 and Q3. The charge across each capacitor is equal. And then for capacitors which are connected in parallel, we have 3 capacitors here. And then it's also connected to a battery. So this diagram here, or this circuit here, is equivalent to this circuit here, in which the combination of 3 capacitors is equal to the equivalence capacitance, which is Ceq here. And then the voltage supplied will be equal to the total voltage. And the total charge Qt is also equal to the total charge of this circuit. So let's try to do the same thing as we did for the capacitors in series. Electrons will flow out from the negative terminal of the battery, moving throughout the circuit, and then it will reach this junction here. And what happened is that the charges will split off. From here, charges will go to C3, and this will flow here, and this will flow here. So as you can see, the total charge will split off at the junction and then flow to each capacitor. The total charge is not equally distributed across each capacitor. And this is why if we try to find the total charge for capacitors in parallel, we will get the total charge to be equal to Q1 plus Q2 plus Q3. Okay, let's look at example 2. In the circuit shown above, calculate the charge on each capacitor and also find the equivalent capacitance. So from the figure, we can see that we have 2 capacitors, C1 and C2, and these capacitors are connected in parallel. As we know, when capacitors are connected in parallel, the potential difference across each capacitor will be the same as the supply voltage. So we know that for parallel, the total voltage is equal to V1 equal to V2. This total voltage is the same as the supply voltage, and supply voltage is from the battery. If you look at the question, we are given the supply voltage here, which is 50 volt. So from here we can also find the voltage for capacitor 1 and capacitor 2. V1 will be 50 volt, V2 is 50 volt as well. But wait, what's the purpose of finding the potential difference when the question is not asking us to find the potential difference? Well, that's because for question A, you want to find the charge on each capacitor. So you want to find Q. So to find Q, you have to use the formula Q equals to CV. And then we know the value of capacitance because the question has given us the value of C1 and C2, but we don't know the value of potential difference. So that's why we have to find the value of potential difference before we can answer this question. So we want to find Q1 first, which is the charge on capacitor 1. So the formula will be C1V1. C1 is 1 microfarad. So 1 times 10 to the power of negative 6 multiplied by V1, which is 50. And then you will get Q1 equal to 50 times 10 to the power of negative 6 coulomb. And then we want to find the charge on capacitor 2. So Q2 is equal to C2V2. And then C2 is 2 times 10 to the power of negative 6 multiplied by 50. And you will get Q2 equal to 100 times 10 to the power of negative 6 coulomb. Or you can also write this as 100 microcoulomb. And then for B, you want to find the equivalent capacitance. So CEQ or CF. So you know that for capacitors which are connected in parallel, you can find C effective by using the formula C1 plus C2. And we are already given C1 and C2. So C1 is just 1 micro or 1 times 10 to the power of negative 6 plus C2, which is 2 times 10 to the power of negative 6. And then you will get C effective, which is equal to 3 times 10 to the power of negative 6 farad. Let's look at example 3. So we have a circuit where we have two capacitors which are connected in series, and the question asks us to calculate the equivalent capacitance, charge on each capacitor, and also the potential difference across each capacitor. So let's start with the first question. We have to find CEQ or CF. So from the figure, we can see that C1 and C2 are connected in series. So we know that if we have capacitors that are connected in series, we will get a formula to find the CF, which is 1 over CF equal to 1 over C1 plus 1 over C2. And then the value of capacitance are given, so just substitute in. C1 is 1 times 10 to the power of negative 6 plus 1 over 2 times 10 to the power of negative 6. And you will get CF equal to 0.667 times 10 to the power of negative 6 farad. For question B, we want to find the charge on each capacitor, so Q. So as we know, when capacitors are connected in series, the charge on each capacitor will be the same, which means that the charge on capacitor 1 will be equal to the charge on capacitor 2, and it is also equal to the total charge QT. Now, what we have to do is to find QT. So to find QT, you have to use the formula of capacitance, which is C equals to Q over V. It's just that you change the formula to be in the form of C effective is equal to the total charge over the total voltage, and then you have C effective, which is 0.667 times 10 to the power of negative 6 equal to QT. VT is given in the question, which is 50 volts, and then you can find QT. So you will get the total charge to be equal to 3.33 times 10 to the power of negative 5 coulomb. And this is also the same value for Q1 and also Q2. And then for C, we want to find the potential difference across each capacitor. For capacitors which are connected in series, the potential difference for each capacitor will be different. So what we have to do is we have to find the potential difference individually. So we want to find the potential difference across capacitor 1 first, C1. So what we have to do is use the formula V1 is equal to Q1 over C1. Q1 is 3.33 times 10 to the power of negative 5 divided by C1, which is 1 times 10 to the power of negative 6. Then you will get the value for V1, which is 33.3 volts. And then you want to find V2, so it is Q2 over C2. And then Q2 is 3.33 times 10 to the power of negative 5 divided by 2 times 10 to the power of negative 6, and you will get V2 equal to 16.65 volt.